We've now covered the basics of covariance and correlation. You can see that correlation improves on covariance as a measure of association by standardizing covariance. And then correlation, as a result, gives us a measure of association that incorporates not only the size or direction, but also the magnitude or strength. However, correlation, and by extension covariance, still have a few problems. You need to be very careful about how you use correlation. And we're going to talk about some of these problems in this part of today's lecture. So one way to kind of look at this issue is to look at what we call Combs Quartet. So he was a famous, or is a famous statistician, and he created 4 sets of variables. And these variables, in essence, they show the limits of measures of association when you just have sort of some kind of numerical summary. And the key point here is that you shouldn't neglect graphical displays, and you should also think about the assumptions of a measure of association, such as covariance and correlation. In particular, these measures of association, covariance and correlation, they capture linear relationships, straight line patterns in a set of data, in essence. They do not capture non-linear relationships. They're sensitive to outliers as well. So let's look at Combs Quartet. Here's his data set. And you can think of this data frame or data set as partitioned into 4 subsets, 4 quartets. And so the first set of data just consists of x1 and y1. And the correlation between these 2 numerical variables, it's 0.816. If we look at x2 and y2, the correlation between these 2 variables, also 0.816. The correlation between x3 and y3, these 2 columns, again, the correlation is 0.816. And then the correlation between x4 and y4, again, it's 0.816. So at this point, you might say, OK, we're done. Right? These variables, they're all pretty much the same. The correlation is the same. Each variable has a positive linear relationship, an extremely strong positive linear relationship. And so we expect as x1 increases, y1 increases. And it's the same pattern for x2 and y2, x3 and y3, and x4 and y4. So at this point, OK, we're done. But we have to be very careful. Right? There are patterns in the data that correlation and, by extension, covariance are missing, because these are just basic measures of association that assume a linear pattern in the data and also assume that there aren't any kinds of outliers that are skewing, that are misleading us in terms of the data. So let's look at Combs Quartet in more detail. So here's the first data set, x1 and y1. Okay, the correlation is 0.816, of course. And then when we create a scatter plot, you can see that, OK, it looks like what you expect with a positive linear relationship. As x1 increases, y1 tends to increase, and vice versa. OK, so here, correlation and, by extension, covariance, it seems appropriate. There's an extremely strong positive linear relationship between these 2 variables. But let's look at x2 and y2. Again, the correlation is 0.816. But look, if you look at the pattern in the data, this is what we call a nonlinear pattern. Nonlinear patterns tend to look like curves or squiggly lines, whereas linear patterns tend to look like more straight line sorts of patterns in a set of data. In this case, correlation is misleading because the relationship in the pattern in the data is in fact non-linear. So the correlation here, it's not capturing the true pattern in the set of data. There's not this relationship where x increases and then y increases. We can see that that occurs for the first half of the scatter plot. But then as x2 increases at a certain point, y2 actually decreases. Right? The correlation is missing that. The correlation is suggesting x2 increases, y2 increases. x2 goes down, y2 goes down. Well, in fact, at the sort of second half of the scatter plot, as x2 increases, y2 actually dips down a bit. So correlation is misleading because it captures a linear relationship, but in fact, in the pattern of the data, we see this non-linearity. If we look at the next set of data, x3 and y3, again, the correlation is 0.816. But if we look at the scatter plot, you can see that we have this outlier. We have an extreme value with respect to y3. Okay? So here, this outlier, it's overstating. The effect of this outlier is to overstate the relationship if you just look at the correlation coefficient. So the correlation coefficient of 0.816, it's much higher than the actual pattern in the data because of that one outlier. So here, the correlation coefficient suggests, well, as x2 increases, as x3 increases, y3 increases, and vice versa. Well, that's true, but there's that one outlier, and if you look at the rest of the data, that correlation coefficient, if you just remove that outlier, would be much smaller than 0.816. Here's a box plot for our variable of y3. And if you recall a box plot, it's very, very useful for finding outliers because a box plot is constructed based on quartiles. Right? And so when we use quartiles, when constructing the box plot, quartiles, they're resistant to outliers. And so here we see that we have this one outlier beyond the whisker on the right-hand side of the plot. And that outlier is in fact problematic because what it's doing to the scatter plot, and by extension to the correlation coefficient, is it's misleading us. It's inflating the correlation coefficient. So if we just look at the numerical summary, we're going to think there's a stronger linear relationship than in fact there really is. If we look at the next quartet, of x4 and y4, the sort of final data set in his quartet, we get this correlation coefficient of 0.816. Right? This is a really weird scatter plot because you can see that x4, right, it only has two values. Right? You can see most of the data points are on the left-hand side, and then we have this one outlying data point in terms of x4 all the way on the right. In a similar way, you can see that y4, most of the data points are kind of lower, and then we have this one outlier in terms of y4. So you can think of, for this set of data, for this scatter plot, we have a data point that is an outlier with respect to both y4 and x4. Okay, that's that data point in the upper right-hand quadrant, in the upper right-hand corner of the scatter plot. Okay, a correlation coefficient for this data set, right, it's very misleading because you can see that this correlation coefficient of 0.816, right, it's based on that one outlier. And in fact, if you remove that one outlying point and just look at the bulk of the data, it doesn't really look like there's any sort of variation in x4. And by extension, there's really no relationship. There's no correlation between these two variables. Right? So here's Anscombe's quartet. We have these four data sets. Right? If we can kind of think of our data frame as partitioned into x1 and y1, x2 and y2, x3 and y3, and x4 and y4. And each one of these scatter plots has a same correlation coefficient. Right? Yet the actual patterns in the data, the actual scatter plots, they're different. Right? And so that sort of overall measure of association, that correlation coefficient, it masks, it misleads. And it misleads because the correlation coefficient is in fact sensitive to outliers. Right? That's because the correlation coefficient and by extension the covariance, they're both based on the means. And the mean, as we know, is sensitive to outliers, and by extension, so is the correlation coefficient and covariance. In addition, covariance and correlation, they capture linear patterns in the data, roughly straight line relationships. And so here we have not only outliers, but some nonlinearities. In the second quartet, x2 and y2, we have this sort of pattern that looks kind of like an upside down U. So the important point here is that you should always graphically examine your sets of data and be careful about correlation covariance being sensitive to outliers. Another limitation of correlation and, in a similar way, covariance, is that they are measures of association. Right? They do not tell you cause and effect. Right? So if you look at past studies, we know that there's a strong linear relationship based on correlation between the number of teachers in a school district and the number of failing schools. And so you might look at that association, you might say, well, the more teachers you put in a school district, the more schools that you have failing. Well, got to be careful, because that's just a measure of association. Could be that if you have a lot of failing schools, the government starts putting more resources into those failing schools through more teachers, right? So this measure of association, right, you've got to be very careful about cause and effect. Studies have also shown that the number of cars in California per year and the number of homicides are related, right? So more cars, more homicides, right? But you've got to be careful about that, because the causal direction could go any sorts of ways. You could also have a lurking variable that is actually in the pattern of data. We also have a correlation between the length of kids' feet and reading ability. The main point is that correlation and similarly covariance, they do not imply or suggest causation. So here's a comic strip, and one person says to another person, I used to think correlation implied causation. Then I took a statistics class, now I don't. Sounds like the class helped. Well, maybe. The key point here is that sometimes life is a little bit more difficult, because as you learn more about reality, you have to be careful about how you interpret what seems to make sense to you. So you look at a correlation, question whether or not that association is in fact misleading, because there might be some other lurking variable, or perhaps in fact it may seem like a causation is going on, but in fact there's actually some other factor going on. The question then is, how can you make causal claims? Well, we talked about this earlier in this course, but and we'll talk about it again, but when we talk about causation, right, we typically use randomized controlled trials or experiments. These are commonly used in medicine, psychology, and biology. And the idea is that you randomly assign observations to either a treatment or control group, and the treatment is some kind of intervention. You give a person a pill, you relocate a person. Right? The idea being that you try to change what's going on in the world to look at how this intervention or treatment affects some outcome. Causation is very, very difficult to establish for certain based on any given particular study. And so when we use correlation and covariance, we often base it on observational studies. Right? Often it's based on not some sort of intervention in the world, but we just have some sort of pattern in a set of data, and we have this measure of association. So be very, very careful about interpreting correlation in a way that suggests causality. And if you really want to establish cause and effect, look at experimental designs. So things to know for this part of this week's lecture. Correlation, it gives us the direction and strength or magnitude of a linear pattern in a set of data. In contrast, covariance just gives the direction. Correlation, it ranges between -1 and +1. That's because when we divide covariance by the standard deviation of x times the standard deviation of y, the units of covariance drop out. Right? And then we have correlation, it's unitless. And both covariance and correlation, they can be misleading, because covariance and correlation, they're based on the mean of x and the mean of y. And the mean of x and mean of y, they're sensitive to outliers. And so covariance and correlation, they are sensitive to outliers. As well, they are potentially quite misleading if the actual pattern in the data suggests some kind of nonlinear relationship is going on, some sort of upside down U, or some sort of squiggly lines, some sort of curve. And the other point is that covariance and correlation, they are measures of association, not causation. If you actually want to find cause and effect, a better approach, rather than looking at a correlation coefficient or the covariance, is to create an experimental design. And with that, we conclude our discussion of correlation, and we will turn to other topics related to numerical data in just a moment.